What's the deal with helium-3? Could helium-3, an isotope found on the moon, be the future of our energy? It sounds like a plot from a sci-fi movie, but the possibilities are fascinating. This unique isotope often appears in films, but in reality, scientists and engineers are seriously considering how helium-3 could revolutionize the way we generate energy. Is it really possible? Let's start from the beginning. Where does helium come from, and why is helium-3 special? Helium is one of the lightest and most abundant elements in the universe. Most of the helium on Earth is helium-4, a stable isotope with 2 protons and 2 neutrons. In contrast, helium-3, the star of this discussion, has just 1 neutron. This small difference is what makes it so intriguing. Fun fact, helium is a noble gas, which means it doesn't form chemical bonds with other elements. On Earth it exists in trace amounts. It literally escaped into space billions of years ago. That's because Earth's atmosphere and magnetic field effectively block incoming helium from the sun. However, it's a different story on the moon. With no atmosphere or magnetic field, the solar wind, a stream of particles ejected by the sun, deposits helium-3 directly into the lunar regolith, the layer of dust covering the moon's surface. Helium-3 as the fuel of the future. Helium-3 is an incredibly attractive potential fuel for nuclear fusion reactors. Why? In standard fusion reactions, like those involving hydrogen and tritium, you get a lot of energy, but also harmful radioactive waste. In contrast, a reaction between helium-3 and deuterium, heavy hydrogen, produces immense energy without radiation or waste. The only byproduct is a proton, a subatomic particle that can easily be used to generate electricity. For comparison, nuclear power plants using uranium fission have an efficiency of about 35%. Fusion power plants running on helium-3 could potentially achieve efficiencies of up to 70%. This means reactors fueled by helium-3 would not only be greener, but also far more efficient. How much helium-3 do we need? It's estimated that to meet the annual energy needs of the United States, the world's largest economy, only about 25 tons of helium-3 would be required. That doesn't sound like much, does it? However, to extract just 1 ton of helium-3, we would need to heat and process about 200,000 tons of lunar soil. This presents a monumental logistical challenge. Fortunately, the moon is thought to contain anywhere from several to tens of millions of tons of helium-3. If we could develop efficient methods of extraction and transportation, we could meet Earth's energy needs for hundreds, if not thousands of years. The race for the moon picture. This, landers, probes and robots digging into the moon's surface. All to extract helium-3, the element that could revolutionize energy production on Earth. Sound futuristic? This scenario is already unfolding. The world's greatest powers are engaged in an unofficial race for dominance on the moon. China's Chang'e 4 mission, which landed on the far side of the moon in 2019, was a major technological achievement. It was the first mission of its kind in history, aimed not only at studying lunar regolith, but also testing technologies that could be used in future resource extraction. The United States isn't sitting idle either. NASA's Artemis program, aimed at returning humans to the moon, is laying the groundwork for a permanent human presence on its surface. NASA plans to build a lunar base that could serve as a gas station for future space missions and as a hub for helium-3 extraction. Fun fact: despite having a smaller space budget than the US or China, India also has ambitious plans. In 2019, their Chandrayaan-2 probe nearly landed on the moon, and their future missions promise to be even more advanced. India sees lunar exploration as a pathway to joining the elite club of spacefaring nations. But let's consider, is this race solely about technology and science? Or is it a new form of geopolitical rivalry? In human history, control over resources has often led to conflicts. Could lunar exploration become another stage for international tension? Or, more optimistically, could it foster global cooperation? Future technology. tokamaks and ITER. Tokamaks, devices capable of controlling plasma at temperatures of hundreds of millions of degrees, are a testament to our technological ambitions. ITER, the largest project of its kind being built in France, is a monumental endeavor involving nations from around the globe. How does a tokamak work? Inside it, extremely high temperatures enable nuclear fusion. Plasma, a state of matter similar to gas but ionized, is confined by powerful magnetic fields. ITER aims to demonstrate that such reactors can not only work but also be efficient. Fun fact: ITER is designed to achieve an energy gain factor of Q(10). This means the reactor would produce 10 times more energy than it consumes to sustain the reaction, a groundbreaking step toward practical fusion reactors. However, ITER is just the beginning. Other projects, such as stellarators or alternative fusion designs, may prove even more effective. But are we ready to invest billions in a technology that might not deliver results for decades? This is a question not only for scientists, but also for policymakers. Did you know that one of the biggest challenges for tokamaks is cooling their magnets? They often rely on liquid helium to bring the temperature of superconducting magnets close to absolute zero. Ironically, even in the pursuit of helium-3, traditional helium technology plays a vital role. Obstacles and challenges. While the vision of an energy utopia powered by helium-3 is enticing, the reality is far more complex. Here are some of the main challenges. Cost of extraction and transport. The Moon is 384,000 kilometers away. Extracting helium-3 would require advanced infrastructure on its surface, from mining equipment to systems for separating helium from regolith. Then it would have to be transported to Earth. Fusion technology. Even if we can extract helium-3, what's next? Today's tokamak reactors are still experimental. We don't yet know if controlled and cost-effective fusion of helium-3 and deuterium is achievable. Geopolitical issues. Should helium-3 resources belong to all humanity, or only to those with the technology and means to extract them? A lack of international regulation could lead to conflicts. Fun fact: current international law, the 1967 Outer Space Treaty, prohibits the appropriation of celestial bodies by any state. But what about corporations? Could private companies take control of helium-3 extraction, just as they dominate resource extraction on Earth? Conclusion: when will the energy revolution happen? It's hard to give a definitive answer. Does helium-3 have the potential to revolutionize energy? Absolutely. Will it happen in the near future? Highly unlikely. Here are a few possible scenarios. If an economical fusion process is developed, helium-3 could become the primary energy source by the end of the 21st century. Alternative energy sources like solar, wind, or next-generation nuclear reactors might develop more quickly and prove more practical. Helium-3 exploration could serve as a catalyst for developing other space technologies like Moon or Mars colonization. Let's ask ourselves, are we ready for an era where resources from beyond Earth become an integral part of our economy? Or is helium-3 just a stepping stone toward even more revolutionary discoveries?